Hi everyone. When I introduced the weak force in the context of the quantum field theory, I mentioned there's this weak boson. This weak boson has a negative charge. Well, we actually expect another weak boson with a positive charge to mediate the opposite reaction as well. And in fact, anytime we go up and down that periodic chart we had, we're going to exchange one or the other of these W bosons. But I also mentioned you can go laterally across the periodic chart as well. Well, that's going to involve a weak boson that doesn't have any charge at all. That's called the Z boson. So actually, there are three particles, three bosons, that mediate the different ways in which the weak force transforms these fundamental particles. And when we talk about how the Higgs mechanism is rolled into the quantum field theory of these initially massless bosons, the way it has mathematically its effect is essentially mixing together these different bosons into what we see in the laboratory today, and basically creating these three bosons. The problem is that in order to get this to work, you really need four. And so we expect four bosons, but we only see three. Now there's a hint, a clue actually, that something else is going on, because the weak bosons, the W's, are electrically charged. And that's the hint that we have that there's some sort of connection between the weak nuclear force and the electromagnetic force. And actually, the photon is the fourth particle that makes up the complete package for the description of the weak nuclear force. In a sense, the electromagnetic reaction is a holdout, a spin-off of the weak nuclear force. And that's what's called electroweak unification. And that's really what the Higgs mechanism has done for us, that the discovery of the Higgs boson verifies this concept of electroweak unification, that these four bosons, which initially are massless, mix together, giving three that carry the mass associated with the Higgs boson and leaving the fourth without it. And according to the theory, this is the predicted mass of these various bosons, and this is the measured mass. And you can see a fantastic correlation there. And so this is a huge success for the electroweak unification, and this is one of the reasons why people really did expect to see the Higgs boson even before it was discovered. It was kind of a foregone conclusion that it would be discovered. If it hadn't been discovered, there were alternate theories, but the Higgs mechanism is by far the simplest one. And so people were really happy that essentially that completes our understanding of the weak nuclear force, and thereby completes our understanding of the Standard Model. So really, in a fundamental way, there are only two forces. There's the strong nuclear force and the weak nuclear force. And only at kind of low temperatures do we really see a distinction made between the weak nuclear force and the electromagnetic force. And that's really because the electromagnetic force, because that remaining fourth boson has no mass, it can interact at a much larger range. And that's what makes the electromagnetic force distinct from its weak partners, is that it's massless, therefore long range, and we experience it as electromagnetism. But at a fundamental level, these are the same. And what happens is at very high temperatures, I mean, we're talking about Big Bang type temperatures, nothing that's experienced in the laboratory today, 10 to the 15 Kelvin type temperatures. That the long range and short range characteristics kind of become moot, because everything's moving around so fast, everything's interacting with everything else. And so the distinction between the two kind of washes away, and at that Big Bang type level, you really only have these two fundamental forces at play. And of course there's always gravity. So fundamentally there are three fundamental forces at the fundamental level.